Hi everyone, and welcome to this lesson on conditional probabilities as a probability function. So the big claim in this lesson is that if we fix a particular event f with the probability bigger than 0, then the function p of events given f from the event space to 0, 1 is in fact a probability. So what this is saying is if you condition on an event, you can treat the probability of events given that particular event, one fixed event, as a probability itself, meaning you can use things like inclusion-exclusion, for example, on conditional probabilities. So it's kind of convenient. Conditional probabilities are a little unintuitive and a little confusing to work with, but you can treat them in a sense as just probabilities. So let's go through the proof first, that this is in fact true. And remember that a probability satisfies three things. First of all, it has to go from the event space to 0, 1. But of course, this function is going to take in events, and the probability of an event A given another event f is always between 0 and 1, because it's still a probability. So there's nothing really to check there. We need to check the other two facts. Another fact about probabilities is that the probability of the whole space is 1. So let's check that even if we condition on an event f, the probability of the whole space is 1. And that's what we're going to check first. So by definition of conditional probability, the probability of an event given f is the probability of the event intersect f divided by the probability of f, even when that event is the whole space. Now this omega intersect f, that's everything intersect f, or elements that are in everything and in f. Well, of course, that leaves you with just f, right? Because if it's all elements that are in f and they're elements, in a sense, like they're elements in everything, then it just means elements in f. So omega intersect f equals f, and that's what's going on from here to here. We can just replace omega intersect f with f. Then we have p of f over f, which is just 1. So we could cancel p of f over f and get 1. And therefore, the probability of the whole space given the event f does in fact equal 1. And that's what we wanted to show first of all. The second property that probabilities have is that if we take a sequence of disjoint events, a1, a2, and so on, then we need for the probability of the union of those disjoint events to equal the sum of the probabilities of those events. And so we need to check that that's also true for these events whenever we condition on a certain event f. And it's actually just going to follow from the fact, well, a few things we have to rearrange with set theory, and then the fact that this is a true statement for probabilities. So this big statement here is what we're trying to check. Let's start with the left-hand side. So we're taking the probability of the union from 1 to infinity of ai conditioned on f. And using the definition, that means the probability of the union from 1 to infinity of ai intersect f divided by the probability of f. Now this is just a set theory fact, which we're not going to check here. But if you take the union from 1 to infinity of ai and intersect this whole union with f, it's the same as intersecting each one of the events with f and then taking the union. Because this statement means take all the stuff in the AIs and then throw out anything that isn't in F, right? Just keep the stuff that's in F after we union up all the AIs. This means take all the stuff in the AIs that's also in F and then union them up. So we're still going to get everything that's in the AIs that's also in F. And so therefore these two things are equal. And that's the point, is that this is an equality. So we're just going to replace the numerator up here with this equivalent statement here. So we write this as the probability of the union from I equals 1 to infinity of ai intersect f divided by the probability of f. And a1, a2, a3, and so on is a sequence of disjoint sets, right? That's what the claim is on a probability, is that the probability of the union of disjoint sets is the sum. And that means that their intersections are all empty, right? So for example, a1 intersect a2 is empty. And if we were to draw pictures of that, that means like a1 would be here and a2 would be here. Well, now we're intersecting all these sets with f. So if I have some big set F, maybe it looks like that. Well, here's A1 intersect F. I just colored in. And then you could color in A2 intersect F, so the stuff that's in both A2 and F. And of course, those sets are also disjoint, because they're even smaller than the disjoint sets that we started with. So the sequence A1 intersect F, A2 intersect F, and so on are also disjoint. And therefore, the probability of the union of those sets is the sum of the probabilities. And that's what gets us this first equality. So we can replace that union with this sum. And that's because now we're not conditioning on anything, right? This is just a regular probability. The probability of the union of a bunch of disjoint sets is the sum of the probabilities of those sets. And because of the way addition works, right, if we have A, that's funny looking, A plus B over C, I can write that as A over C plus B over C. So it's just a little rule of algebra. That's what's going on in this line. So I have the sum, a bunch of stuff added together, all divided by P of F. And then I'm just going to instead write this up as adding them all up together of each term in the sum divided by P of F. So it's like taking each one and putting it over the denominator and adding them all up. And finally, each one of these pieces here is by definition a conditional probability. So the probability of AI intersect F divided by the probability of F is the probability of AI given F. And so therefore, we have shown that this is in fact true. So the probability of the union of the AI's given F, which we started with, is equal to this thing we worked it down to, right? The sum from I equals 1 to infinity of the probability of AI given F. Okay, so that was definitely the more complicated part. That's the proof. Let's look at an example. So you're given a table of information about a survey that was given to test some ice cream flavors. So adults and children were allowed to taste lemon-flavored ice cream, a berry-flavored ice cream, and we recorded whether they liked the lemon, whether they liked the lemon only, or the berry only, or whether they liked both. So the question is, what is the probability that an adult likes at least one of the flavors? Well, let L be the event that a person likes lemon only, and let B be the event that a person likes berry only, and let E be the event that a person likes both flavors. We'll let A be the event that a person is an adult. And here what we're curious about is the probability that they like both, or they like berries, or they like lemon, given that they're an adult. Now, L, B, and E are disjoint events, right? So one is lemon only, one is berry only, one is both. And we just showed that if we condition on an event, such as the person's an adult, this is in fact a probability. So the probability of a union of disjoint events is the sum. Therefore, the probability they like lemon only, or berry only, or both is the sum of the probabilities. The probability they like lemon only given they're an adult, plus the probability they like berry only given they're an adult, plus the probability they like both given they're an adult. And these values come from the table. So the table says for an adult, the probability they like lemon only is 5%. And so we're going to say the probability that they like lemon only, given that they're an adult, is 0.05. And the probability they like berry only, given for an adult, is 34%. So the probability they like berry only, given that they're an adult, is 0.34. And similarly, the probability they like both is 0.32. So we can just add up these numbers, 0.05 plus 0.34 plus 0.32 is 0.71. There's a 71% chance that an adult will enjoy at least one of these ice cream flavors. So that was our lesson on the fact that whenever we condition on an event and the event is fixed, you can't condition on different events and treat them as a probability. But if there's one event, it can be treated as a probability. It's not the case if the left-hand side is fixed. So you can't take the probability of F given different events and treat that as a probability anyway. I mean, you can take F given different events, but it's not a probability. So let's look at a counterexample to show that you can't do this. So consider the outcome of two coin flips, and F is the event that the first flip is a heads. So F is the event, heads heads or heads tails. A is the event that both flips are heads. So A is heads, heads. And B is the event that the first flip is a heads and the second flip is a tails. So B is the event heads and then tails. The sets A and B are disjoint. So if we could treat probability of F given some sets as a probability, then we should be able to do the probability of a union of disjoint sets is the sum of the probabilities. So in other words, the probability of F given A union B, this should be equal to the probability of F given A plus the probability of F given B. However, all of these events have probability 1. So if we're given A union B, which means that either heads heads or heads tails occurred, we know F occurred because F is either heads heads or heads tails. If heads heads occurred, then F occurred because F includes heads heads. And if heads tails occurred, then F occurred because F includes heads tails. So the probability of any of these conditions is 1. However, the probability of F given A plus the probability of F given B equals 2. Oh, sorry, this should be a plus sign. So if we add up the probabilities, we get 2, which is of course impossible to be the probability of F given A union B. So you can't split up a union of disjoint sets into a sum on the right-hand side. That's the last of these fundamental lessons on probability that I have right now. The next lesson, we should get into random variables. So I'll see you there.